بسم الله الرحمن الرحيم الصلاة والسلام على رسول الله الأمين. السلام عليكم ورحمة الله وبركاته. In this video, I will show you some simulation results regarding the envelope detector wake operation, as I have promised you in the previous lecture. Before that, let us recap on the working operation of the envelope detector. And as shown here, the circuit diagram that represents the envelope detector, which consists of a simple diode, capacitor, and a resistance, RC filter. And the input voltage is the modulated wave or the AM signal. So on the positive half cycle of the input signal, the diode is forward biased and the capacitor charges rapidly and to the peak value of the input signal. When the input signal falls below the value or this value, the diode becomes reverse biased and the capacitor discharges slowly enough through the load resistor. This discharging process continues until the next positive half cycle. When the input signal becomes greater than the voltage across the capacitor, the diode conducts again and the process repeated. All right, so now let's simulate this envelope detector and let me show you some simulation results. So in the simulation software, I have built this detector circuit, this envelope detector circuit, along with a low pass filter, RC, low pass filter, and a DC blocking capacitor, And here at the input, I have applied the AM signal, and hence I have selected the modulation index of the AM signal to be 0.8, and the carrier frequency is 100 kilohertz. So this is the carrier frequency FC of the modulated wave, while the AM signal or the input signal frequency or the message signal of the frequency FM is equal to 1 kilohertz. So the carrier frequency FC is much greater than the input or the message signal frequency. Moreover, I have selected the value of this R and C in such a way that the condition which we have discussed is already getting fulfilled. So if you see the RC time constant, then it is equal to 50 microsecond, while the carrier frequency is equal to 100 kilohertz. That means if you see 1 over FC is equal to 1 over 100K, that is equal to 10 microsecond. That means the RC time, the RC time constant, is greater than the 10 microsecond. It's greater than 10 microsecond. That means the RC time constant is greater than 10 microsecond. Moreover, if you see this input signal frequency, then it is equal to 1 kilohertz. So 1 over Fm is equal to 1 millisecond. And this time constant, RC, is much less than 1 millisecond. That means the condition for the detections of the AM signal is already getting fulfilled. So first of all, now let me show you the AM signal. Then after, I will show you the detector output. So let us click on the oscilloscope and run this. So here, this is the waveform of the AM signal, as it shows in green color. This is the waveform of the AM, or the modulated signal. Now, let me show you the output of the envelope detector. So if we run the simulation once again and show you the AM signal along with the output of the envelope detector, we will get this signal. So this blue waveform is the output of the envelope detector. And as you can see, there is some ripples in the output. So by using the low pass filter, we can remove these ripples. So here I have connected a simple RC low pass filter, and the cutoff frequency of this low pass filter is selected in such a way that it should be able to pass the message signal. So let us see the output of the low pass filter. Let us simulate this. So the red waveform is the output of the low pass filter, and because of the low pass filter, there will be some phase delay, but we are able to recover the message signal. And if you pass this filtered output, the red waveform, through a DC blocking capacitor, then we can remove the DC offset. So after the RC filter, a 1 nanofarad of DC blocking capacitor is used, and the output is measured across the 1 mega ohm resistor. Now here the value of this DC blocking capacitor should be selected based on the load value, because if you see over here, this RC will make a high pass. This RC will make a high pass filter with cutoff frequency equal to 159 if you calculate it hertz. That means it will pass the message signal and it will remove the DC component. So if we see the output across this load, then it will look like this. Let us run the simulation. You see? So this red waveform shows the output after the DC blocking capacitor. So in this way, by properly selecting the values, it is possible to recover the message signal or the information signal that has been sent from the transmitter to the receiver. So this is the extracted signal. Now, if the RC time constant is not properly selected, then we will see some distortion in the output. So first of all, let us make this RC time constant very small. So here, instead of 0.01 microfarad, we select the value of the capacitor as 1 nanofarad, and this is the case. And let us see the detector output. Let us run this simulation again and see the output. So this is a case. This blue waveform is the output across the capacitor. It is the output across the capacitor. And if we zoom in, then as we can see, there is a more ripple in the output. That means if the value of the RC is very small, then the capacitor will discharge rapidly. Now let us show the other case when the RC time constant is very large. So for that, let us make this capacitor as 0.1 microfarad, and let us show the output. So let us start the simulation and see the output. So in this case, as we can see, the detector output is not able to follow the envelope, and because of that, there will be a distortion in the output. That means the value of this RC should be selected properly. So now, finally, let us show the case when the modulation index is greater than 1. So let us make the value equal, mu equal to 1.5. So in that case, the modulated output will look like the following waveform. Let us run this simulation again and look at the values. And if we see the recovered signal, that is the output across the detector, then as you can see, it looks different. So if we pass this red signal, or the output, the blue signal, or the output of the detector through the low pass filter, then there will be some distortion, as you can see here, in the recovered signal. That means this envelope detector circuit works perfectly only when the modulation index of the AM signal, or the modulated wave, is less than 1. That means mu is less than or equal to 1. So I hope in this video you understood the working principle of the envelope detector. Thank you very much. I'll see you soon.